Lindsey, and this is the Floating Tape Lab. So first, an introduction. The purpose of this lab was to determine the amount of excess or deficient charge on one piece of tape and to determine the force exerted by one U-tape on another when they were measured a certain distance apart. And we also wanted to observe and record the interaction the two pieces of tape had on each other and discuss the sign of the excess or deficit charge on the levitating tape. A key finding was that the charge magnitude on each tape was 2.23 times 10 to the -8th coulombs. And so for materials, we had a tape measure, clear tape, a flat surface, two books, and a recording device. And for the procedure, we essentially stuck two pieces of tape together and we rubbed them. And then we fixed one piece of tape on between two books. And then we slowly lowered the other tape until the two pieces of tape attached, where one was in our hands and one was on the book. And then we also measured the distance before we brought the pieces of tape together as well as after to use for later calculations. Now to talk a little bit about measurements, and also to the right is a picture of kind of our setup. We had the length of each tape being 0.1778 meters. And to get the mass, we just took this and multiplied it by, took this length and multiplied by 0.001 kilograms per meter, because this is, you're given that this was kind of what we should use for the tape. The distance between the tapes until levitation was 0.02794 meters, and the floating separation, or like the separation we started, was 0.0508 meters. And here are some model computations. If you want to pause the video and look at them a little more closely, I just copied them straight from my glow script code. And the weight force and electric force are the same, except of opposite sign. So there were a few key assumptions that we had to make in order for this lab to kind of be physically, I guess, possible. And one of the assumptions was that there was a point charge in the center of each piece of tape. We modeled them as 2 point charges interacting, and that each piece of tape had the same amount of net charge evenly distributed across its surface. And also we assumed that air resistance was negligible, as well as the swinging of the tape, although we tried to keep the tape pretty stable in our hands as we did the lab. And here are a couple calculations and key physics concepts that you have to understand in order for this lab to make sense. First of all, when the tapes stuck together, like one of them started levitating, you could assume that the total force in the system was equal to 0, which allowed you to set the electric force equal to the gravitational force. And the equation to the right represents the electric force on tape B due to tape A. And we also assumed that the charges on each tape were considered equivalent. And so that allowed us to take this magnitude equation, just do Q squared. And then we could rearrange this equation to get the charge on Q. And this depended on our distance. So here's my model as well as my code. To the left, you can see just the actual representation of my model, where the cyan arrow represents the electric force on the tape, where the green arrow represents the weight force, the gray rod in between is the distance, and the red sphere is, and the purple sphere are both point charges, where the purple sphere is tape B. And to the right, I have my constants, and to the bottom, I have my computations, where it's just I have the computations of, the electric force, the magnitude of the charge, the number of electrons, all of those types of things. So first we found the charge on floating tape B, and we took that equation from before, plugged in our numbers, and we found it to be 2.24 times 10 to the -8th coulombs, and we found the electron deficiency on the floating tape of B to be 1.4 times 10 to the 11th electrons, where 1.6 times 10 to the -19th, we got that number just from the elementary charge of the electron. And as well as the fraction of atoms giving up electrons, we found the area of the tape. And then we found the number of atoms on the surface of the tape by dividing this area of the tape by the area of an atom. And that we were given the area of an atom. And finally, we took the ratio between these two numbers and found the fraction of atoms giving up electrons was, or the electron kind of deficiency in each atom was 4 times 10 to the -7th. So a couple questions. If the electrons had positive charge and protons had negative charge, the signs of all the charges would be reversed, but the observations would be the same. Like charges would still repel and opposite charges would still attract. And it's important to handle the charge tapes as little, with kind of as little as possible, because touching the tapes allows the charge to flow to or from your hand and nearby objects, which can neutralize or reduce the tape's charge and weaken or eliminate the electrostatic effects that you're trying to observe. And finally, as far as conclusion goes, the purpose of this lab was to again view the way point charges interact with one another and determine the amount of excess charge on one piece of tape. And by observing the distance and mass of the pieces of tape we used, we were able to quantify the amount of excess charge on one of the pieces of the tape. And in order to make the tapes hover on one another, the electrical and gravitational forces had to be equal. And we found that tape B experienced 3.3 times the electric force at that distance where they started levitating in comparison to the beginning distance. Thank you so much.